In this video, I'm going to talk about the solubility equilibria in continuation, and in this video I'll talk specifically about determining whether you form a precipitate given a reaction in water. But first I wanted to go over a couple of just kind of remind you about some fun facts when it comes to solutions. Okay, so you can have three different scenarios. If you have a solution that's been formed under normal conditions, right, just adding an ionic solid to some water, you have three different scenarios that can happen, right? The first scenario is where you have in this solution here, you add just a couple of ions, or just enough solid for a little bit of the ions to go into solution, right? And this was called an unsaturated solution. Now you could also have this scenario where if you're adding some sort of ionic compound to a solution, you can max out how much of that ionic compound will go into the solution, right? So into the water. So these red dots indicate the ions that have dissolved into the water, okay? And so once you've maxed out that solubility, right, you have achieved a saturated solution here, a saturated solution. And now the third scenario under normal conditions is such that if you have this same water, right, you've maxed out all of the ions that can go into that solution at that temperature, right? But then you go just a little bit further beyond that, and then you have some solid that's collecting down on the bottom of your solution, right? So you have this in tandem solid and dissolved ions in your solution at any given point. And so this is beyond saturation at that point. So this is saturated plus solid. Saturated plus solid. Okay, now mathematically, we actually have a way to determine whether or not with an ionic compound that has a low solubility, we can tell whether or not which of these three scenarios will achieve, okay? And we do that by good old Q. Remember, Q is our reaction quotient, and it is taking into account the concentration of our ions in solution without being at equilibrium, right? Not necessarily at equilibrium. Because remember, when we are at equilibrium, our Q is equal to our K, okay? So when you have an unsaturated solution here, your Q is actually less than your KSP for any given solid. That is to say that the molarity of the ions is so low such that you have not reached the maximum amount of ions that will go into solution at any given time. So you end up with an unsaturated solution at that temperature, okay? So your Q is less than your KSP. If you have a scenario where you have a saturated solution, your Q, this is when you're actually at equilibrium, and your Q is equal to your KSP. This is actually what you guys saw in lab when we were dealing with the potassium nitrate in water, and we were heating it up, and right when you saw that solid form, you took the temperature of it, right? And so right when that solid, just before it started to form, that's when you had a fully saturated solution, which is when we were at equilibrium. So if your Q is equal to your KSP, you are just on the edge of being able to form solid in your solution, but you are at a saturated solution at that point. You've maxed out the amount of ions that can go into solution at that temperature, okay? Now, the final scenario is when you have the saturated plus solid, right? There's precipitate in your solution, and your Q is actually greater than your KSP. That is to say, you have more ions that are accounted for, right, than KSP will allow, if you will, for those ions to go into solution. Okay? All right, so let's work a problem. Let's apply this a scenario. Okay? So right here I said predict whether a precipitate will form when 250 milliliters of 0.004 molar barium chloride is added to 650 mils of 0.08 molar potassium sulfate. Okay, so the first thing you want to do here is set up what the potential scenario would be. Okay. So if you were to form the products, right, since these are all ions, you have barium 2 plus 2 Cl minus, right, and then 2 potassium ions, and then a sulfate ion. Okay, so our possible scenarios here. We could form KCl, or we could form barium sulfate. Okay, now KCl, and this would be a 2 in front of the KCl in order to balance equations, right? So a 2 KCl and the barium sulfate. So this is when you would actually look back at your solubility guidelines to see which one would likely come out of solution. That is, which one is insoluble in water. KCl is most definitely soluble in water, so this would actually be, this would remain in solution as their constituent ions. This guy, though, barium sulfate, actually ends up being the solid that you would potentially form, okay? Now, if that's the one that we potentially form, then you go look up what the KSP for that particular compound would be, and in this case, the barium sulfate actually has a KSP of 1.1 times 10 to the minus 10. And this is actually something that you would look up like on a table, or I would actually provide this information for you on an exam or something. Okay, so now we want to look to say, okay, the concentration I have of both of these in solution, all right, and compare it to the KSP to see whether or not a precipitate will form. Okay, so first we're going to look at what our barium concentration is. Okay, so you have 250, you started with 250 milliliters, right, of this 0.004 molar solution, right? But now the concentration, because we have increased the volume, we're actually going to take the total volume here. So you had started with 250 milliliters of the the barium chloride, and then you also have in there 650 milliliters of that potassium sulfate. Okay, so once you do this calculation right here, this calculation right here gets you to the number of moles, right, that of the barium that you're adding, right, and then this volume gets you to your total liters. So then if you do moles divided by liters, you end up with molarity. And then this, so the barium ion, its concentration added from the original solution was 0.0011 molar. Okay, so now let's do the same thing for the sulfate. So we're going to take the volume of the original sulfate solution times the molarity divided by the total volume again. And the overall concentration for the sulfate ion, 0.0058 molar. Okay. So now we can actually set up the reaction quotient, right, to see what the whole, what the Q of this particular scenario would be. So remember, our reaction quotient here will just be the concentration of barium times the concentration of the sulfate ion. right? And because they're in a 1-to-1 ratio, we don't have to raise it to the power of any exponents or anything. Don't have any exponents for either concentration. So if we multiply 0.0011 times 0.0058, right? Your Q actually ends up being 6.4 times 10 to the minus 6. Minus 6 there. So notice if you're comparing, so this is the concentration of your species in solution, right? So this is your Q right here. This is the Q of this particular scenario. Now notice that it is larger than your KSP by quite a bit, actually. Larger than your KSP, indicating because this is larger than your KSP, you do in fact form precipitate if you were to mix barium chloride at 0.004 molar concentration with the 0.08 molar concentration of potassium sulfate. Precipitate formed. And you would form a precipitate and solid would come out of solution. And that is how you can predict whether a precipitate will form given two species in solution, two ionic species in solution.